This is Heather Connor, and this is part 3, the final part of my 3-part series for the Fun with Sticky Tape experiment. We've completed 2 experimental trials with our pieces of Scotch Brand Invisible Tape, showing that we were able to charge the pieces of tape. One would become negatively charged, one would become positively charged. We showed that when we took one of these negatively and positively charged pieces of tape and put them close together, that we had attraction, and when we put 2 of these same charged pieces of tape close together, we had repulsion, where they were pushing away from each other. Now is my attempt to explain what was going on. So all matter is composed of atoms, and in an atom, this is my simplistic little model, obviously 2-dimensional as opposed to a 3-dimensional atom, but we have a nucleus that would be here in the center, and the nucleus contains the mass of the atom, all the protons and neutrons, which are neutrally charged neutrons, or positively charged protons, are contained in this nucleus, and they're held in the nucleus and they can't really travel around very much. Around outside the nucleus, though, you have negatively charged particles called electrons. They have a negative charge, the electrons do, and very, very little mass. Pretty much enough, small enough that we can not consider it as contributing to the overall mass of the molecule. And these electrons are outside of the nucleus and are able to move about much more freely. In fact, electrons are able to even be transferred among atoms, and that's how we get some of our bonding between different types of atoms to form certain molecules. We can have ionic bonds, where a positively charged molecule is bonded to a negatively charged molecule, or we can have covalent bonds where those electrons are shared. But when we're talking about static electricity, what we're doing is we're talking about the transfer of these electrons between atoms. I remember being in elementary, middle, and high school, and we had these big bar magnets, and these are much larger than what we had. But they had different poles on them. They had positive and negative poles. And we used to do kind of a mini experiment about what would happen when we tried to put the 2 poles together. So if you had a positively charged pole here on the inner side and a negatively charged pole here on the inner side, and you put them together, they would stick together pretty strongly, and it took quite a bit of force to pull them apart. That just showed, it's a good illustrative way to show that the oppositely charged attractions attract each other, the oppositely charged ends attracted each other. Conversely, when we would turn those bar magnets over and we had the 2 positively charged or the 2 negatively charged sides, poles, facing each other, when you tried to put them together, it would be a good deal of force would be needed to put them together. Then as soon as you let up on that force, they'd slide apart or they push each other apart. And that's a good illustration of how the same charges will cause repulsion and will push each other away. So kind of a little simplistic model, but I think it's good illustratively. So what happens when we're doing the static electricity, and what happened with the tape, is that when we put them together, we were charging one of the pieces of tape, and the electrons were moving from one of the pieces of tape to the other, and there were positive and negative charges on the pieces of tape, so that when you put a T and a B together, they came together, but when you put a T and a T, they actually pushed away and had a repelling effect because the 2 were negatively or positively charged. We don't know for sure which one is negative and which one is positive, but we do know that they were the same charge because they repelled each other. It's very similar to when we have a balloon and we rub on our hair. What we're doing is we're charging the balloon, and now the balloon is more negatively charged than your hair. Your hair is more positively charged. And you get the hair being attracted to the balloon. I have a lot of hair, so there's a lot of attraction going on. I shock my husband every winter when we walk through the house and then touch each other. You can almost see it, like a little electrical current even occur sometimes between the 2 of us, but you see all of the electrical charge in the balloon, which is negative, attracting the now positively charged hair. Same thing can occur with things other than a balloon, like a hat. For example, in one of the neat resources for the week, one of the other class participants had a website that talked about like putting a hat on and taking it off and how your hair could just be sticking up everywhere. Same kind of thing when you put a shirt on and maybe you take your shirt off or put it over your head and your hair's sticking out to every which way because of the static electricity that's built up. So in this case, we had static electricity build between the 2 pieces of tape. That resulted in them being attracted to each other if they were oppositely charged, or repelled by each other if they were negatively charged. What was very interesting about this experiment was, in doing crime scene work, which I've done in the past, we lift latent prints from a scene by using a wider piece of tape. It's very similar to Scotch tape. It's a lot more expensive because it's forensic kind of tape. But What's funny is when I would lift, I would actually fold over to have a little handle too, so I wasn't getting my prints on the tape, but that's neither here nor there. But so what would happen is we would have this piece of tape out in the field, and you would put the tape on a surface, and you'd rub it out, and then you'd pick the piece of tape up, and then you would take a latent lift card, which would be just like a 3x5 card like this, except it's glossy, and you would try to put the piece of tape on the card, and it would immediately like suck right onto there, and that's due to a static electricity building up from rubbing the tape on the surface from which the print is being lifted. So that is a great way to think of how it applies to my everyday life, because you would have to be very careful about how you approached the lift card with the lift tape so that you didn't have the tape stick like in the middle and be off on the side, because you always wanted your tape to go across the lift card. I thought I had some actual lift tape and cards to show what I'm talking about, but I wasn't able to find it, so maybe in a future video I can show that. But I thought this was a great simplistic experiment that was very powerful in just seeing how static electricity works, how you charge an item. It was interesting. I thought when I tried to use the charged pieces of tape and put them on things like the wooden coaster or the pottery mug, and I'm wondering if it seemed like some of the pieces of tape were much more attracted to some of the materials than others, and I wonder if that's not a um, result of the type of material that we're seeing if the tape is attracted to, such as wood versus metal. Metal is obviously very conductive, and electrons can travel very well through it, whereas wood may not be quite as conductive and may be more insular. Plastic is the same kind of way. So my assumption from this, or my conclusion, would be that the more conductive an item, the more attraction you may see between a charged item and this other item you're putting it next to, such as the soda can, for example. So I hope this is what you were looking for as a physical model of what happened between the interactions that we experimented with. And I will see you next weekend in my weekly summary following this. Thank you very much. Bye-bye.